It was published in the scientific reports in the Nature portfolio. So a little bit about peripheral artery disease. It's a common circulatory problem where the arteries to the limbs are narrowed and the blood flow is reduced. And it's also common cardiovascular disorder that is frequently undiagnosed. So some typical symptoms of this disease are pain in leg and hip while walking, pain in arms, and leg numbness when and weakness, and some other symptoms. Well, I try to make it like high level without too much technical stuff. So in terms of the population for the peripheral artery disease, it affects 8 to 12 million American adults and more than 200 million patients worldwide. And 12 to 30% of these patients are above 65 years old. So the limitations of the diagnosis of this disease, that the current risk models are, first of all, limited to area under the curve of 0.8. And this is because they modeled only demographic data, laboratory data, comorbidity, but they don't model the lifestyle of the patients. They can't also, which is like time sequential data, time series data, and also biological factors. So another limitation of this of the diagnosis of peripheral artery disease is the lack of implementation, where 68% of surveyed primary care didn't perform measures that are, they know that they are, it's important for the diagnosis process. As example, ankle branchial indices, although 89% of them knew that it's one of the predictive features. And this is because the lack of time, the lack of staff, and lack of financial reimbursement. So the challenges in the diagnosis of this disease is that only 10 to 30% of the patients report the typical symptoms, which make it harder, to diagnose it. And only 25% of surveyed adults showed awareness of this disease. So the goal of this research was to improve the ability of automatic detection of the peripheral artery disease using electronic health record data. And when we use electronic health record data, we can actually model lifestyle factors. We model what happened to the patient all over his history, and also we can model biological factors. So, and this actually would help in a more timelier medical improvement and optimization, and would improve the long-term outcomes. So for existing research, the state of the art that was like before this work, it was like Duval and colleagues defined risk factors and used logistic regression to predict patients with high versus low risk for peripheral artery disease. And some of these risk factors or comorbidities are hypertension, hyperlipidemia, diabetes, coronary artery disease, cerebrovascular disease, and others. So some other work that tried to use natural language processing for the diagnosis of peripheral artery disease patients. So they developed using natural language processing rules to extract keywords that would describe PAD, peripheral artery disease, and their accuracy was around 81.8. So for the data set and cohorts, so what we had in terms of cases for PAD, we had around 3,000 cases. And for the control, we had around 17,000 cases. And this data was taken from Stanford electronic health record data from 98 till 2020. And of course, we split the data 80 to 20%, like 80% training, 20% for test set. And for mimicking the behavior and the prevalence of this disease in the electronic health record data, we use the ratio of 1 to 10 because this is the prevalence of the peripheral artery disease patients. So we can, when we try to train a model, we mimic the real situation. And so for including patients as those that has a peripheral artery disease, what we did is the criteria was to every patient that has at least 2 diagnosis or mention of ICD codes, CPT codes with peripheral artery disease. That's how we at least two diagnoses over the data, and we included only data that is prior to 60 days. So we don't include kind of predictors of the disease, and and also patients that had 1 year and more of history. Only patients that had more than that are 50 years and older. So some cohorts characteristics, we saw that 70% of the entire cohort, it was in Stanford, so 70% were Caucasian, 60% of the PAD patients were male, and 45% of the control were males. And for the high burden morbidity comorbidities, we found that 40% of the PAD patients had cerebrovascular disease, and 72% had coronary artery disease. And some other disease that occur with this disease were heart failure, hypertension, diabetes, and hyperlipidemia. So if we look at some of the features that we used for the model, as example, if we try to see what features are significant, so we used the t-test for continuous variables and chi-square for categorical variables. So as example, the age, we found that it's significant. We had the p-values lower than 0.05, and we can see that the average age was almost 75 years in the cases and 67 in the controls. We can see that in race and ethnicity, the Caucasian was not a significant feature in terms of like the predictiveness of the features. The Black was significant, Asians and Hispanic was not. So for the in terms of the disease that the patient had, So we see that cerebrovascular disease was significant, coronary artery disease, and heart failure, hypertension, diabetes were all significant. The BMI was not that significant, and if the patient is a current smoker, then it was a significant feature. So what we did in this research is we took 3 different models, and we evaluate their capability of automatic diagnosis and in peripheral artery disease. So we used the traditional risk factors with logistic regression for on our dataset. So we ran all 3 models on our same dataset so we can compare them. We used random forest, which is ensemble learning, which uses actually different learning models, and then build the score out of these models. So in this case, it's random forest, so it has multiple decision trees. The input features for this model was the electronic health record data features. We tried also recurrent neural network as a deep learning model, which can model sequential data. So I'll talk a little bit about the RNN, recurrent neural network, because of its ability to model sequential data, which it fits our needs, because we need to model the visits, information that appear in the visits of the patients, and this has sequential behavior, so we use the RNN. So for the RNN, there are multiple variations. The problem with the main RNN is, our simple RNN, is that it tends to forget on long sequences. So we use other variation, which is LSTM, long short-term memory. So and this actually overcome the limitation of the vanishing gradient. So as for the features that we use, the data that we were trying to incorporate in the model, we used during the visits, we incorporated diagnoses, procedures that the patient had to have, observations, medications, and we combined each one of those data, or we call it kind of contextual data, with the age of the patient on that visit and the recency in days since the day that we are doing the evaluation. So this is the architecture in high level, like one of the architecture, the deep learning architecture, where, as we can see, we used LSTMs that modeled the visits, the sequential data. And as we can see here, in each time step, we use the concept IDs, where concept IDs, in this case at Stanford, we had it, each one of the observations, the diagnoses, procedures had a unique concept ID, and the type of this concept, as example, as I said, diagnosis or procedure, and also the recency. And then we can see here also, we modeled also the patient information, as example, the current age where we are doing the prediction, the race, the gender, and one of the features that we thought would be helpful was the average number of codes that the patient had all over his history. We used fully connected neural network for the patient information, LSTMs for the sequential data, and then we used binary classifier that would predict whether the patient would develop peripheral artery disease or not. So if we look at the ROC curve for the deep learning models, we can see that we had 5 folds actually, and then we calculated the AUC and we drew the ROC curve, ROC curve, and then we can see that in this case the 5th fold performed best. And to measure the reliability of these models, we also did calibration curve, and we can see here that each one of the models for the folds was well calibrated. I think there was a multiplier. Yeah, and then taking time to move between them. Okay, so this is the logistic regression where we modeled the risk factors that were defined by other research, and it's kind of prior knowledge. So we can see that it was performing relatively lower than the deep learning model, and it's not well calibrated. So let's see. And then we have the machine learning model that also used the electronic health record data, same as the data for the deep learning, and different from the data that was modeled in the logistic regression approach. And we can see here that it was also performing well, but the deep learning was much better. And it's also not that calibrated. So we tried to measure the relationship between how sophisticated is the model with the true positives. And we can see here in this table that the logistic regression is the least sophisticated model. We can see that compared to the random forest, we had like 9.6% more true positives. In the deep learning, 24.6% added, like improvement of 24.6%. For the random forest with deep learning, it was 13.7%. And if we look at the most predictive features that we extracted from the random forest model, we can see that the post-procedural state was the most significant. The essential hypertension, the next one, abdominal aortic aneurysm, hyperlipidemia, and we see down the list features like cardiovascular symptoms, chest pain, dyspnea. So here we compare the performance of the models. So we compared with metrics AUC, area under the curve, specificity and sensitivity, and we see that, and we took like average of the 5 folds. So for the logistic regression, the AUC was 0.811. As you can see, the deep learning was outperforming all the rest. Also in sensitivity, which is how correct do we predict true positives. And we can see that we have 0.95, which is very high. And it's much better than the other algorithms. And the specificity, we can see that it's also performing much better than the rest. So for the specificity, it's how good do we label those that didn't have PAD as correctly. So in addition to building the models, we thought that it's important to do kind of study with surgeons in Stanford and primary care physicians. And we showed them two different visualizations. So one visualization was showing the confidence of our decision, and we are saying here we are saying that 83% we are confident that this patient should like the surgeon or the physician or the primary care physician should do the screening for the PAD. And then we had some links where they can explore more risk factors and some NLP summary of the recent visits, like a textual summary of the recent visits, and some demographics. The other visualization, we try to reduce the number of clicks till the user to be able to get more comprehensive overview about the patient. So we had the demographics already in the first, let's say, just to be clear, this is the first screen that the user would see. This is one thing, and the other visualization for the same study where users saw two different visualizations, and then we got feedback from them. So in this case, we show the risk factors. As you can see here, also we show like diabetes, it's red, so he doesn't have it. And then the hypertension, so the patient doesn't have it. Hypertension is, he has this disease. And then we are, in this case, you don't see the score, but we don't recommend to do the screening because we are confident that the patient doesn't have a PAD. We have also some summary that we extracted using natural language processing with AI. And then we measured multiple themes. So we tried to look at the ease of understanding of the system, the ease of use, the acceptability, and as example in the ease of use, 6 out of 12 they showed kind of difficulty in understanding the models, so they wanted probably a more intuitive or needed some some explanation before using the system. For the ease of use, we saw that 7 out of 12 participants showed and believed of the importance of incorporating electronic health record data, and 8 out of 12 thought that we should reduce the number of clicks. So the second visualization was more, they tend to have to like the second visualization which will have all the information in this first screen. And then for the acceptability, so peripheral artery disease, some of the primary care physicians thought that it's not that, acute if they don't measure it. So 4 out of 12 thought that, and the rest thought that it's important to help in this screening using artificial intelligence. And then we had 2 out of 12 didn't believe that much in machine learning. The rest believed that, the machine learning and AI would help in this, in their process of the diagnosis. Yeah, so that's it. I tried